Hello and welcome to the YouTube channel D Creations Resources. Today let us talk about the experiment regarding the mass absorption coefficient of a material. So first of all, let us understand what is the mass absorption coefficient. It is a measure of how effectively a material absorbs a radiation per unit of mass. And it has applications in several areas such as radiation dosimetry or shielding and protection, etc. And it is given by linear absorption coefficient divided by the material's density. So its unit can be centimeter square per gram or meter square per kg, where you do understand that centimeter square or meter square will be unit for cross-sectional area and gram or kg will be unit for mass. So an experiment to measure this mass absorption coefficient will involve having a beam of radiation. So say for example beam of beta particles passing through absorbers of known mass per unit area or known thickness. Now this material could be even aluminum. So you have a beta source such as strontium, 38 is its atomic number and 90 is its mass number, and that is going to emit beta particles and they are going to pass through absorbers of aluminum, and these absorbers will be of different thickness. Now obviously you have to have a detector after the absorbers. So that detector can be a GM counter. So basically the Geiger-Müller detector, which is used for detecting and measuring ionizing radiation such as that of beta rays. Now in case of the absorber, you can obtain its mass thickness by multiplying the density by the physical thickness. So if physical thickness is in the unit of length, for example say in centimeter, obviously it is going to be very small, but when you say centimeter, if you are multiplying it by its density, so again if I take CGS unit, as you know density is mass per unit volume, so say gram per centimeter cube, so it is going to lead you to gram per centimeter square. That is going to be the mass thickness. Now in the experiment, initially you will find out the count without using any absorber. So in a way you are measuring the initial radiation intensity, and then you would place a set of absorbers of increasing thickness between the source and the detector and measure the transmitted intensity. So if it is in terms of counts, then you will find the natural algorithm of these, and that will be plotted on y-axis versus the mass thickness on the x-axis. So slope of this line is going to give you mass absorption coefficient, and of course where it cuts the x-axis, that intercept is going to give you range. A little bit about the GM counter. So a Geiger-Müller tube is a metal tube filled with an inert gas, for example argon, at low pressure, and high voltage is applied between a central wire-like anode and the cylindrical cathode. And usually along with argon you will also have a quencher such as ethyl alcohol. Now when beta particles are going to enter this tube, they are going to collide with the argon atoms and they will knock off electrons and create ion pairs. Now this high voltage is going to rapidly accelerate these free electrons towards the anode wire, and on their way they will collide with other gas atoms creating more ion pairs. So this is kind of a cascade effect, and it is called Townsend discharge, or it's also called an avalanche. And this avalanche is going to produce short measurable electrical pulses, and whatever is the device's electronic circuitry, it is going to process this pulse and it is going to record. Now the use of quenching agent, as I said, like for example ethyl alcohol, is to stop the continuous discharge after each pulse, allowing the tube to reset for the next radiation event. Now you may be aware that the linear absorption coefficient can be calculated using Beer-Lambert's law. So when radiation passes through matter, its intensity is going to decrease exponentially. So I will be equal to I0 e raised to minus mu x, where I0 is initial intensity, I is the transmitted intensity, mu is the linear absorption coefficient, and x is the thickness of the absorber. So from this you may know mu, and then when you want to find out mass absorption coefficient, it is mu divided by rho, where rho is the density of the absorber. So if you compare the linear absorption coefficient and mass absorption coefficient, you will understand that linear absorption coefficient is intensity loss per unit thickness, that is per centimeter. So its unit is centimeter inverse, while mass absorption coefficient is the intensity loss per unit mass, that is per gram, and its unit is going to be centimeter square per gram. So the linear absorption coefficient depends on the material's density and its atomic composition, while mass absorption coefficient is independent of the density. It depends only on the atomic composition of the material. So this is the advantage, that if you use or if you know the mass absorption coefficient of a material, then it is more of fundamental property, because it answers the question that suppose if you consider two materials, lead and wood, and in case of linear coefficient, linear absorption coefficient, you would say that suppose there are two blocks 1 centimeter thick each, and one is for lead, one is for wood, and lead is much denser than the wood. So the radiation is going to be much more attenuated by lead. The linear coefficient is high for lead as compared to wood. But now if you compare the mass absorption coefficient, it answers the question that if I have the same mass of lead and wood, which one is better absorber? So you are dividing the linear absorption coefficient by the density to get mass absorption coefficient. So this property is of the material's atomic structure and not how tightly packed it is. That's why it is preferred, because you can use it for comparing the absorption properties of very different materials as well. Now, this concept of mass absorption coefficient is important for several applications. For example, in medical imaging, even if you think of X-rays, and then if you visualize an X-ray taken, you will understand that there is a contrast difference. So bones, which are made up of calcium, which is higher atomic number, appear white on an X-ray, while softer tissues, which is mostly consisting of water, that means low Z, appear to be gray. Now this mass absorption coefficient is very useful for radiation shielding, because you need to know the required mass thickness of materials that are to be used as shield. And usually lead is what is preferred there to use, so that to protect people from harmful radiation in nuclear power plants. It also has applications in X-ray fluorescence and astronomy and astrophysics, etc. So overall, a useful concept. Thank you.